Welcome to the Explainer. Have you ever looked at your C++ code and thought, it's good, but I know it could be great? Well, you've come to the right place. Today, we're pulling back the curtain on the advanced features that really separate solid code from powerful, professional, and rock-solid applications. Time to go beyond the basics. So here's our game plan. We're going to start with the magic of making decisions at runtime. Then we'll peek under the hood to see how it all works. After that, it's all about building resilient code that doesn't break when things go wrong. Then we'll get into writing super adaptable logic and wrap things up by mastering how to copy objects without shooting yourself in the foot. All right, let's dive right into our first big idea, polymorphism. Just imagine for a second you have a bunch of different shapes. You've got circles, squares, triangles, you name it, and you want to tell each one to draw itself. How do you write a single piece of code that correctly calls the right draw function for each shape, especially when you don't even know what the shape is until the program is actually running? That is the exact problem that polymorphism is here to solve. Okay, check this out. Here's the problem and the solution, plain as day. On the left, without that virtual keyword, we're calling a function through a base pointer, and it calls the base version every time, even if the object is actually something else. It's just wrong. Now look at the right. We add one simple keyword, virtual, and bam, the program is suddenly smart. It knows the object's real type at runtime and calls the correct function. That, right there, is polymorphism in action. So what is this magic virtual keyword actually doing? Well, a virtual function is you, the programmer, telling the C++ compiler, hey, hold on, don't lock in which version of this function to call right now. Wait until the program is running, figure out what the actual type of the object is, and then make the call. This whole idea is what we call late binding, and it is incredibly powerful. And this difference is absolutely crucial. You've got two camps here. On the left, you have early binding. This is the default in C++. The compiler sees a function call and hard codes it right then and there. It's fast, but it's totally inflexible. On the right, you have late binding, which virtual gives us. This is the opposite. It waits. It gives us that runtime flexibility that makes polymorphism possible. Now, you're probably asking, okay, how does C++ actually pull off this late binding trick? Is it just magic? Well, no, not quite magic, but it is a really clever mechanism that's happening behind the scenes, and it's all thanks to something called the virtual table, or VTable for short. This diagram lays out the whole clever system. See, when you create an object from a class that has virtual functions, the compiler secretly tucks a hidden pointer inside of it. We call it the VPTR. And notice where that VPTR is pointing. It's not pointing to a function. It's pointing to a shared address book for its class, which we call the VTable. And that table is just a list of the correct virtual function addresses for that specific class. The key thing to realize is that the compiler does all this for us. So when you make that virtual call, the program just follows the object's VPTR to the right VTable, looks up the correct function address, and makes the call. That two-step lookup process is called dynamic dispatch, and it's the engine that makes polymorphism go. All right, let's shift gears and tackle our next big skill, writing code that doesn't just fall over when something unexpected happens. How do we handle those runtime errors with grace, without crashing or, worse, leaving a huge mess of leaked resources behind? I mean, think about this classic programming trap. Your code is running great, everything's fine, and then it's asked to do the impossible, like divide a number by 0. What happens next? Well, if you don't have a plan, the answer is usually a spectacular program crash. And, the crash itself is bad enough, but the really scary part is what gets left behind. If your program just dies, any of that important cleanup code you wrote, to close a file or release a network connection, it just gets skipped. And that leads to resource leaks, which are these silent, nasty bugs that can make your whole system unstable over time. Thankfully, C++ gives us this awesome 3-part safety net called exception handling. It's simple, really. First, you wrap any risky code in a try block. Second, if something goes wrong in there, you throw an exception, which is basically just an object that describes the problem. And finally, you write a catch block that's ready and waiting to, well, catch that specific problem and handle it, letting your program recover instead of crashing. Okay, let's talk about a different kind of problem. We've talked about runtime surprises, but what about the predictable, mind-numbing repetition in our own code? You know that feeling when you find yourself writing the exact same chunk of logic over and over and over again just for different data types? This is such a classic example. You need a function to swap two values. So you write one for integers. Cool. Then you need one for doubles. So you copy, paste, and change the type. Then you need one for strings, so you do it again. The logic is identical every single time, but now you have 3 functions to maintain. If you find a bug, you have to fix it in 3 places. Ugh, there has to be a better way. And of course there is. Enter the function template. We take all of that duplicated code and replace it with this one single elegant function. It's a generic blueprint that can work with any data type we throw at it, and the compiler automatically creates the specific versions for us as we need them. It's brilliant. So what exactly is a function template? Honestly, the best way to think of it is as a recipe, or maybe a cookie cutter for your code. You define the logic, the shape of the cookie, once. Then, whenever the compiler sees you trying to use it with, say, an int or a string, it just uses that cutter to stamp out a perfectly specialized version of the function for you. It's all about writing less code that does more work. All right, for our final topic, we're going to uncover a subtle but really dangerous bug that can sneak into your code when you start copying objects that manage their own resources, like memory pointers. By default, when you copy an object, C++ just does a simple bit-for-bit copy of its data. We call this a shallow copy. And for simple objects, that's totally fine. But if your object has a pointer in it, a shallow copy is like photocopying the key to your house. You now have 2 keys, but you still only have 1 house. And this diagram shows exactly why that's a disaster waiting to happen. After that shallow copy, you've got 2 objects, sure, but look closely. Both of their internal pointers are pointing to the exact same block of memory. So what happens when the first object gets destroyed? Its destructor frees that memory. But wait, the second object's pointer is now pointing at garbage. It's a dangling pointer, and the second you try to use it, boom, your program crashes. The right way to handle this is with a deep copy. Instead of just copying the pointer, the key, we allocate a brand new separate block of memory for the new object. Then we copy the data from the old location to the new one. So now, instead of 2 keys to 1 house, we've built a whole new identical house and given the new object its own key. They are completely independent and safe. So how do we actually do this? It's a pretty clear 3-step recipe. And you usually write this logic inside a special function called a copy constructor. Step 1, copy any size info. Step 2, allocate brand new memory for the object you're copying to. And step 3, copy the data from the source over to that new memory. That's it. You've got a true, independent duplicate. So let's bring this all home. Polymorphism gives us incredible flexibility. Exception handling gives our code resilience. Templates make our code reusable and dry. And understanding deep copy makes our programs safe and predictable. These aren't just isolated features. They're the pillars you build professional C++ applications on. They are what will take your code from just being good to being truly great. The real question is, what will you build with them?